negative sign. Okay. Now the angle for the section C2 would be plus pi by 2 to minus pi by 2 if you look at the section C2 considering the direction. Okay. Now when you substitute plus pi by 2 and minus pi by 2, we get the angles, and so section C2 maps to a circle of radius 0. Now why radius 0? Because the magnitude comes out to be 0, or rather very small. Okay. So the complete section C2 is represented by a point at the origin. Okay. Now similarly, section C4. Now section C4 is the smaller semicircle where the radius is epsilon, which tends to 0. Again, substitute S is equal to epsilon e raised to j theta depending on the radius. After substituting, we get 5 upon epsilon e raised to j theta, then two different brackets after substitution, and then again we do the same thing. Again, the 5 upon epsilon, after taking these two common, again we get epsilon raised to 3, right? So that step is skipped on the slide, but you can very well understand. So this 5 upon epsilon comes out to be infinity, okay? Because epsilon is as good as 0. Then when angle is minus pi by 2, because for section C4, now the starting point of the angle is minus pi by 2 and the end point is at pi by 2 depending on the direction. So after substituting this angle, we get infinity e raised to j pi by 2 and infinity e raised to minus j pi by 2. So this is nothing but we get a semicircle with the radius to be infinity. That semicircle starts at pi by 2. It ends at minus pi by 2, right? So section C4 maps to a semicircular area of radius infinity and angle varying from plus pi by 2 to minus pi by 2. Is that okay? Okay. Now the complete Nyquist plot for section C1, C2, C3 and C4, if you combine all sections, we get this Nyquist plot. Now please try to understand the next step, what we are going to follow. After sketching the Nyquist plot, our task is to calculate n. Okay, n is nothing but number of encirclements around the critical point. The critical point lies on the negative real axis, right? And so to understand whether this particular Nyquist plot is encircling critical point or not, we need to understand what this particular point is, which is denoted as omega pc, right? Whether that point is greater than or less than minus 1 plus j0, this point, right? So to calculate this point, what we are supposed to do here, value of omega is 0 because this point lies on the real axis, so imaginary part would be 0. Now, so intersection of polar plot with negative real axis, that is omega pc, can be calculated by equating imaginary part to 0. So in the next steps, what we are doing is we are substituting, we are rationalizing the equation. We know this method, we have studied it before in our curriculums. So by rationalizing this, we are separating out real part and imaginary part. In this imaginary part, again, we are equating the imaginary part to 0 and we are getting this equation. Omega is equal to plus minus under root 2. Okay. Now here, please understand, in polar plot, omega varies from 0 to plus infinity. So negative values of omega are out of our consideration, and that is why value of omega that we are considering is plus under root 2. That comes out to be 1.41, right? Now, even if value of omega is calculated, we still do not know what is the value on the real axis. So for that, we need to substitute omega equal to under root 2 to the magnitude equation, and then we need to calculate it. As we can see on the last line on this slide, we are substituting value of omega and then we are directly calculating the value. Now that value comes out to be 0.833. Okay, so now if you look at the equation, let me put the diagram again. Now, if we put the equation here or the values here, the omega PC is under root 2 and the point at which on the real axis at which this omega PC occurs, this point is 0.833. Okay, so it is still not minus 1 plus J0, right? So minus 1 plus J0 is outside this polar plot, and that is why encirclements around the critical point comes out to be 0. In the previous stage where we have open loop transfer function, we had analyzed the values of z and p, and we have found the value of z is equal to 0 because there were no zeros, and number of poles are 3, but all the poles lie either on the left half of S plane or on the origin. So that is why value of p was also 0. So to satisfy Nyquist criteria, n has to be 0, which from the diagram we can see that it is true, n is equal to 0, and hence the system is stable, right? So we'll just read the last comment of the solved problem. Yeah. So number of encirclements of Nyquist plot with minus 1 plus J0 is 0, and therefore n is equal to 0. By substituting in this equation, we can get z is equal to 0, zeros of 1 plus GSHS if we consider, okay? Number of zeros of 1 plus GSHS lie in right half of S plane are equal to 0. So the system is closed loop stable. Here we analyze the closed loop stability by Nyquist criteria. Now I suggest you to go back to this particular problem and look at the section wise polar plot, right? Because that is the most important thing in this whole method. And ultimately you need to locate the point minus 1 plus J0 and locate the point of intersection of your polar plot with negative real axis, and you can then check whether there are encirclements around the critical point or not. If there are encirclements, you need to count them. That will be value of n, and that value of n should match with minus of p, right? Then only Nyquist criteria will get satisfied and the system will be stable. Okay. If you have any difficulty regarding this solved problem, please get back to me. This was the last part on Nyquist of Nyquist plot topic. So for the previous sections also, if you have any problem, any issue in understanding any concept, please get back to me. Thank you.